Last speaker of this session is Casey Smith from Resonon, who will speak about versatile and customizable hyperspectral imaging machine vision. So the stage is yours.
All right, thank you. Yeah, thank you. My name is Casey Smith. Gonna briefly walk you through some new software that we're just releasing right now for adapting hyperspectral to machine vision. So the outline for today, I'll run you through hyperspectral imaging very quickly, since I think most people in the audience are familiar with it. Discuss why we were motivated to do this, and then show you a walk through the software and some applications. So as you probably know, hyperspectral imaging, depending on how you define it, a continuous reflectance spectrum for every pixel in an image. Most definitions say 100 to 500 different spectral bands per pixel. And we offer ranges, as we'll discuss later, from 330 nanometers in the UV all the way up to 1700 nanometers in the SWIR. Our systems are all push broom dispersive systems. We find that the additional spectral resolution that these systems provide is very useful. And in machine vision applications with a conveyor belt, it's a natural fit on top of that. This is a typical industrial application as it looks in a cartoon. We have a spectral imager and some lighting, a product moving on a conveyor belt, a computer that's doing all the analysis, and then some sort of output device, whether it's a robot or air jets or a database. And to the right there, you can see the actual hardware. So the power of hyperspectral imaging also comes with the drawback in that it's a lot of data to manage if you want the results that you're looking for. And the motivation for us really came down to taking any kind of domain expertise out of analyzing hyperspectral data and just getting to the results that you're looking for. Below you can see some graphs. This was a project that we had looking at picking out almond shells from almond streams. And so I plotted both the spectra of the nuts and the shells on top of each other. And you can see with the red and the black line that the mean spectrum is indeed different, and you should be able to tell the two apart. But if you look at the actual spectra and imagine an envelope around that, it becomes really hard to do. So to the right is the first three principal components. If you're familiar with PCA analysis, a very simple algorithm to try to maximize the variance between different variables. And so the red and the blue in that graph shows the first three principal components. And you can see that there's some hope in trying to separate shells from nuts. And as you add more and more dimensions with your spectral data, you can refine that even better. But the point here is that you don't want your customers to have to know about principal component analysis to solve the problem that they're looking for. You want to automate that in the easiest way possible. So these are our goals. We want it very easy to use with no knowledge of hyperspectral imaging. The training should be very easy and simple and intuitive. Another one of our goals was to have the training happen in the same software package that the runtime happens, so that you don't have to switch between different platforms. And this allows, in some cases, we have customers that are running on a conveyor belt that are running one product in the morning, and then they need to run a different product in the afternoon. And you don't want any training to get in the way of that switchover. Or sometimes even a product comes in on a truck that's a little bit different color than what they're used to. They have to retrain the system on the spot. So we wanted to make it as easy and quick as we could. It runs on Windows and Linux. We have some GPU acceleration in progress at the moment as well. So now if I can figure out how to start the video, I'll run you through how it works. No. Do you know how to start the video? Yeah. Oh, it's not working? Okay. Okay.
Sorry about that.
I apologize. That was the majority of my talk today. But I can run you through the video at the booth later if you're interested. Really, you just label your the objects that you're interested in, whether it's a product that you want passed or a defect that you want picked. You label them on the screen and hit the training button, and that's it. And then it's ready for runtime. The one thing that all hyperspectral machine vision software struggles with is that there has to be one more software layer in between the results, the end of the analysis, and the robot or the airjets or whatever the end goal is. And one thing that Resonon does is that we tackle those problems ourselves a lot of the time. So you don't have to bring in a third-party software integrator to program for your robot. But if you're a machine vision integrator and you're comfortable doing that, then we've made your job easier by providing this software and some nice interfaces that you can program against. The software is compatible with all of our spectral imagers. Like I said, we have a Pika NUV that starts at 330 nanometers. We have 2 different VNIR models, 400 to 1,000, and 2 different SWIRs. 900 to 1700 nanometers. And a few applications. The biggest one for us is plastics sorting and recycling. Being able to determine what type of clear plastic is which so that airjets or robots can then sort them into their right containers. Pharmaceuticals, of course, trying to confirm that the pills in a package are indeed the pills that are supposed to be there. Pretty important problem. And then in the visible and near infrared, we do a lot of food quality control and sorting as well. And a couple examples there in the food regime. And that's it. So I'll show you the video if you want to stop by the booth. We're in hall 10. C40 is the booth number with Laser 2000.
Thank you very much. Hall 10, C30?
Yeah.
40?
Yeah, 10C40. Yes.
10C40. There you can see the video, and of course there you can see the working systems. So check out their booth. Are there any questions? Okay, if this is not the case, then we will end this here. So thank you very much.